Let's continue with the discussion of the orbital parameters that are mentioned in the Surya Siddhanta, the cosmic constants. We have already seen these shlokas in the last video. So let's move forward from there. First thing I want to mention now, point out to you now, is there are two words in these shlokas. One is Shigra and the other one is down here, Manda. What are these words? Now, these two words are here because we are dealing with a geocentric model and not with the heliocentric reality. So, the Hindu astronomers brought the idea of Shigra Ucha and Manda Ucha into their mathematics. The idea of Shigra Ucha, it is a point on the orbit of a Graha where the Graha is moving the fastest. And Manda Ucha is a point on the orbit of a Graha where it's moving the slowest. So they were recognizing the fact that the Grahas move with varying orbital velocity and they were accounting for that in their mathematical model. This is an advanced topic, so I will not look at these two at this point in time. I will ignore them. Secondly, if you look at the first shloka, it says a lot of things. In the Mahayuga, the revolutions of the Sun, Mercury, Venus, and the Shigra of Mars, Saturn, and Jupiter, all of them are moving 4,320,000 revolutions in the Mahayuga. Now, I'm going to focus only on revolutions of the Sun and ignore the rest because the rest are down here. The Moon, Mars, Mercury, Jupiter, Venus, and Saturn are all here. So these are the ones I will focus on. And Sun is here. Now observe that all of these are Graha. But if you come down to verse 34, it's talking about the revolutions of the asterisms. There's nothing but the Nakshatra Mandala. Now, you know from the definition of Graha itself that the Grahas are the ones that move along the Nakshatra Mandala. So we know that the revolutions are all the revolutions of these Grahas round and round the Nakshatra Mandala. But the Nakshatra Mandala itself does not revolve. It's fixed, it's stationary. So what is the shloka talking about? Now, why is the shloka saying that the asterisms are rotating so many times? Revolutions of the asterisms is such a large value. So to understand that, we should not read this as revolutions of the asterism. Instead, we should read it as the number of risings of the asterisms in a Mahayuga is this big value. So what does this number of risings of the asterisms mean? That is nothing but this movement, the actual rising and setting day after day, as we observe from the surface of the earth. This is the diurnal movement, this is the daily movement. And this in our timekeeping is known as Nakshatra Horatra, and the duration of one rising to the next rising is 4 minutes short of 24 hours. And it's known as a sidereal day or Nakshatra Horatra, and this is the basis for further subdivisions like Nadi, Vinadi, Prana. We have seen all this in earlier episodes of Ahargana. So this is the revolution that is being mentioned in the shloka as the risings of the asterisms. So these are the revolutions, the orbital revolutions of the Graha, and for the Nakshatra Mandala, it is known as the risings, the daily rising day after day after day. Good. Now I'm going to change this view into a different format, a format that is more amenable to mathematics, a tabular format. So in this format, I am showing you two columns, revolutions sidereal and risings diurnal. So this is the number of revolutions the Grahas make. Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn. And this is the number of times the Nakshatra Mandala rises in the east during a Mahayuga. Nakshatra Mandala rising means every single nakshatra rises so many times during a Mahayuga. Now what I want to do is, these numbers are so huge, How do we make sense of them? Are these numbers correct or wrong? Is there any way we can compare these numbers with some modern known numbers? That's what I'm trying to uncover. And I will do this in 2 steps. In the first step, I'm going to first find out the number of risings of the sun in a mahayuga, this cell. And how do I find that out? The shloka actually tells you how to do that. Let me bring that shloka back here. So it says, the last shloka says, the number of risings of the asterisms diminished by the number of revolutions of each graha respectively gives the number of risings of the graha in a mahayuga. Diminished means subtraction. So what this is really telling us is, to find the number of risings of the sun, you simply take this minus this. This is the number of risings of the sun in a mahayuga. Because you take the number of risings of the asterisms, that is this, diminished by the number of revolutions of the sun, that is this. And you get the risings, number of risings of the sun in a mahayuga. Now, what does this really mean? Risings of the sun really means sunrise. And if the sun rises so many times, it simply means there are so many days, solar days, right? That's all it means. So these 3 numbers which you see on the top, they are telling you the duration of a mahayuga in different units. This is telling you duration of a mahayuga in sidereal days, or what is known as nakshatra horatra, which I explained is 4 minutes short of 24 hours. This is telling you the duration of a mahayuga in solar days. Savana horatra is a mean solar days because this is an average, 24 hours. And this is telling you the duration of a mahayuga in sidereal solar years, Nirayana Sauravarsha. There is a bit of a problem here in the sense that now I'm saying this is sidereal solar years, but if you remember when I discussed yuga, we started with day and night of the gods, and I said that is a tropical solar year. Now I'm saying this is a sidereal solar year, the same number, Chatvari, Trini, Dve, 4,320,000. But for the time being, let's park that aside and say this is solar years. So all these are durations of a mahayuga. But what's important for us is this, which we calculated just now. And why is it important? Very simple. So you see, what does this line tell us? This line tells us that to make 4,320,000 revolutions, the sun takes 1,577,917,828 solar days. Therefore, to make one revolution, how many solar days does the sun take? This is a very elementary 3rd standard division problem. You take this divided by this. And what do you expect you will get? There you go. 365 and a quarter days. Again, every 3rd standard child will know that a solar year is 365 and a quarter days, but the Gregorian calendar takes 365 and then adds 1 extra year extra day every 4 years in February. So this big number which we started with, 4,320,000 Chatvari Trini Dve, it is actually telling you that a solar year is 365.259 solar days. It's just a different way of putting things. That's all there is. The ancients looked at things differently. And in brackets here, I'm showing you the modern value. Modern value is 365.256. So the ancient value and the modern value had a difference in the 3rd decimal place. 3 points difference. How about the moon? Same reasoning. To make 57,753,336 revolutions, the moon takes 1,577,917,828 solar days. Therefore, to make one revolution, how long does the moon take? Take this, divide by this, and what do you expect to get? You get the 27 wives of the moon. You know that the moon takes 27 days to go completely around the nakshatra mandala. That is why the nakshatra mandala is divided into 27 equal parts called nakshatras. Not exactly 27.322, but we know this story. The modern value also 27.322. So this huge number is the same as saying the moon takes 27.322 days to make a sidereal revolution around the nakshatra mandala. Isn't this like magic? Mathemagic. That's what I call this. Continue with the others. So Mercury, I take this divided by this. Venus, I take this divided by this. Mars, I take this divided by this. Jupiter, the next division, and finally Saturn. And there you go. So these big numbers are boiling down to these much smaller numbers, and all of these are recognizable. You can verify them. You go to Wikipedia or any other scientific website and you will find these orbital periods of the planets. These are the modern values, and you can see the integer values are pretty much matching, except there is a difference here of 10 days. It's Saturn. Everything else matches. Decimal places, there are variations. But this is how accurate the Surya Siddhanta's assessment of sidereal orbital periods was 1600 years back. Now, yes, scholars say that the actual documents available to us of Surya Siddhanta were probably not 1600 years back. I mean, they were probably only 1000 years old. Because the original documents from 1600 years back, written around 300, 400 AD, were continuously modified by others. There was no publisher, there was no ISBN, there was no control over these documents. So people kept updating them. But even then, even if this was 1000 years old, this is a fantastic degree of accuracy of the orbital periods. Now, why is this represented with such large numbers? Why did not they use small numbers? Scholars say the simple reason is they did not want to use fractions. The ancient astronomers wanted to work with integer numbers. So ideally, they should have taken a least common multiple of all of these. But instead, they took a different approach. They said that we will take this cosmology, the mahayuga period, and work with that and set it up in such a way that it reflects for us the actual orbital periods. At least they set up the orbital period of the sun based on the mahayuga, and everything else they added in proportionate fashion to reflect these values. So now you see this makes perfect sense that these big numbers are absolutely accurate. How accurate they are, you can see from here. And this is what I wanted to do in this video to show you. It's not great mathematics. I did just one subtraction and a lot of divisions. But these numbers are the fundamental constants of Hindu astronomy, of the Surya Siddhanta, because all other computations which are made in Surya Siddhanta are based on these numbers, and the accuracy of these numbers determines the accuracy of your further results of determining positions of planets, of determining the time of solar eclipse, lunar eclipse. Everything depends on these numbers in green. And also this one which we calculated now. So you can see how brilliant the ancient Hindu astronomers were. So I will just show you, I will close by showing you a quotation which I got from a book. It's from a bishop of Syria in the 7th century AD, Severus Sebhak. And what he says is, I will not say anything now of the sciences of the Hindus, who are not even Syrians, of their subtle discoveries in the science of astronomy, which are even more ingenious than those of the Greeks and the Babylonians, and of the fluent methods of their calculations, which surpasses words. I want to say only that it is done with 9 signs. What he means is 9 digits, 1 through 9. I can't put it better than this. The fluent methods of their calculations surpasses words.